Okay, so now we look at the example 1. So the question here is asking for find the absolute extremum for the given function on the specific region. So you can see here, the region here is a rectangular region. Okay, so we just focus to get the absolute extrema, whether there is max min, only inside the square region. So you can see that the region is so the region you have, so we just draw it. X is between -1 to 1, okay, and then y also between -1 to 1. So it looks like so this is y explained. So we only interested to have 1, -1, -1, 1. Okay, so if we look at the vertices here, so there is the point, this point, this point, and also the point. So we have to, as you can see here, first you need to provide the critical point for the given function. The process is the same as the local extrema that you done before this. Okay, and then boundary point. So we have here the point here is -1, -1. This is -1, 1, and this one is 1, 1, and this is 1, -1. So that is a boundary point, this one. And then the critical point lies along the line. So you have to obtain the critical point along this. You got 4 lines, right? The boundary lines. So you got 4 boundary lines. So you have to find out if any, if there is the critical point along this line, you have to do that. You have to obtain that. So this one is from the result. So you have to do that process. Okay, so now we want to find out the critical point first. So based on the function given, we have f(xy) is given by x squared minus y squared. So the same as you done for the local extrema before this, you have to find the partial derivative with respect to x equal to x and equate that by 0. And then fy, you have -2y, equate that by 0, and we solve this simultaneously, and you can obtain that you have 0, 0 is the critical point, only 1. So you can see here the critical point is at the origin. So meaning that imagine that you have this kind of surface, whatever chart or whatever shape that you have, you can use the GeoGebra 3D to give you the surface of this, because we never asked you to sketch the surface for this, right? For this question. So, but we just interested to know the max min in this area. Okay, in this area for this given function. So you know that 0, 0 is lying inside the region, so we have to consider that if you obtain that the critical point outside the region, outside this region, so you don't need to count it in, okay, because that was outside the region, so we don't interested on that. Okay, so now the boundary point. So the boundary point, you can see from your sketching here, you got 4 points there, so these are listed here. And then you have to find the critical point along the line. So you got 4 lines there. Okay, so now we look at let's say I give a name. So this is line 1. This is the line 1. So that line 1 is happened at x equal to 1, isn't it? Okay, so now you have to substitute x equal to 1 into the function. So you only have the function f in terms of y only. So you have replaced x by 1. So you have 1 minus 1 squared. And then for this, you have to find the critical point. which means that you have to differentiate this with respect to y. So you got negative 2y and equate that by 0. So you obtain that y equal to 0 and then x equal to 1 by 0. So for this line, the critical point at this line is happen at 1, 0. 1, 0, so 1, 0 is, where is it? 1, 0 here. So it is lying inside along the line, must be along the line because we're interested to investigate along that line. Okay, so that is the one of the critical point, which is this one, 0, 1. Okay, now we move to the line 2. So line 2 is y. This one, y equal to 1. So line 2 is at y equal to 1. So you replace the y equal to 1 into the function. You only have it f in terms of x. So you replace here, y is 1, so you have x squared minus 1. And then we differentiate that with respect to x. You got 2x and equate that by 0. And we obtain that x 0. So we can say that the critical point at y equal to 1 happened at 0, 1. Okay. 1, 0 is here, we done that, and 0, 1 here, okay. And then third line, where is it? Here. So this happened at x equal to negative 1. So we replace x equal to negative 1 into this function. So you have fy, and then x squared, so you have 1 minus 1 squared, and then differentiate with respect to y. So you get negative 2y and equate that by 0. So you obtain y 0. So you can conclude that the critical point along this line is at negative 1, 0. So we have here negative 1, 0. Okay, make sure that that point is lying along the line. If it is outside the line, so we don't count that one. Okay. Maybe you might wonder if is it only one point that happened along the line. It depends. Okay, depends because this one is straight line, so it's not necessarily one. So it depends on the critical point that you obtain. Okay, now we go to the fourth line. So fourth line happened at y minus 1. Okay, y negative 1. So your fx is x squared minus 1. F prime x is 2x, and equate that by 0 because you want to find the critical point, and you obtain that at 0, and we conclude that the critical point along this line is at 0 minus 1, which is this. So we done all the boundary lines for the region. Now we list down all the points, which is this one. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have to evaluate all the function f for these 9 points. So when you substitute that, so you just substitute x 0, y 0 into your function here, okay, and you obtain the function 0, and you list all the things there, and then you find out which one is the most maximum. The maximum one is 1, and the lowest one, sorry, typo here, and the lowest one here is negative 1. That's it. And we can just say that, therefore, the absolute maximum is 1 and the absolute minimum is minus 1. So maybe you might wonder, do we need to justify the points? Okay, you look at the, depends on the instruction. If they just mention find the absolute value, so you just focus on the value. Max is 1, min is minus 1. But if they ask for the specific point, then you have to highlight. So the maximum happened at 1, 0, negative 1, 0, and then that's it. And then the lowest one happened at, so you have to justify. So it depends on the instruction. Okay. Sorry, it did a bit noise, right? There is a noise. It seems to me that my earphone here, microphone here doesn't work. So sorry about the technical problem. Right. Okay, so we look at another example here. So this one, So, okay, find the absolute extrema of the function on the closed triangular region in the first quadrant bounded by the lines given. Okay, so for that one, okay, the function given is f x1 3xy minus 6x minus 3y plus 7, and then you have a bounded region where it is bounded by the lines x equal to 0, y equal to 0, and then y equal to negative 5 over 3 x plus 5. Okay, so I give the solution just in case you didn't understand. That's what from my explanation. So now you have to sketch the graph. So you have 2D region is on 2D on y-axis plane because it is given all in x and y. So you should sketch the region on xy plane. Okay, so lines of x0 is this one. So that is x0, and then y0 is this one, and then you have the straight line negative slope, and this one is supposed to be 5, and this one must be, so you have to set y equal to 0, negative 5 over 3x plus 5, so you have 5 over 3x equal to 5, so x is 3 over 5, so you got 3, so this one is supposed to be 3. Okay, so your region is a triangular region as stated here. Okay, so remember from the previous example, you have to, so you have to list all the possible points. So the first one is the critical point. So based on the function given, to get the critical point, you have to find the partial derivative f respect to x. So for fx, you got 3y minus 6 equal to 0, and you have y equal to 6 over 3 if you do. Is it 3? Okay, and then fy, so you have 3x minus 3, okay, equal to 0, and you obtain that x is equal to 1. So your critical point for the given function is at 1 to only 1 point. So only 1 point. Okay. Okay, now you have to refer this back later, and then the boundary, the vertices. So you got 3 points as the vertex. This one, this, and this. You have to check the value on that 3 vertex. So the point that you have here is 3, 0, and then you have 0, 0, and you have 0, 5. And you have to check that your 1, 2 is lying inside the region. Okay, so to check whether the point 1, 2, the point here x is 1, y is 2, is it lying in the region or not? So we just want to know the 2 here is higher than the line here. I mean that. So what I'm doing is I substitute x equal to 1 into the function y here. So I just want to check whether if I replace x equal to 1 into the y function here, what is the value that I should obtain. So when I replace y1, the highest value here, I mean that, let's say the 1 is here, So the value is 10 over 3, which is 3 point something. So as you can see that from the critical point that we have, the value is 2, which is 2 is smaller than 3.3, right? So somewhere over here, 2 here is smaller than 10 over 3. So meaning that 1, 2 is lying inside the region. So how I check whether the critical point that we obtained at first is inside the region or not. If it is outside, so we don't count that one. Remember that? So we just count whatever in the region. Okay, so now we have 4 points so far. So this is 3 and this is 1. So you got 4 points. And we also need to check, is there any critical point along the 3 lines? So you have the boundary line, you got 3 boundary lines here, so you have to check. Okay, so the first line, this one. Okay, now we check at line 1. So what is the equation there? We have a straight line, right? So you can have that one is at x equal to 0. So what is the function when x equal to 0? So your f in terms of only y becomes, just replace 0, this one 0, this one 0, you have only negative 3y plus 7, and then we obtain the critical point. You have to differentiate that with respect to y. You have minus 3 equal to 0. So there is no critical point. Okay, because obviously there is no derivative here. So it is impossible minus 3 is equal to 0. So there is no critical point there. So we can see that no critical point. Okay, the critical point does not exist. Okay, line 2 is also straight line. This one. So that happen is y equal to 0. So you have to replace y0 into the equation, the original equation here. This one. So this one 0, 0, you have negative 6x plus 7. And then find the critical point if any. So you got negative 6 equal to 0. So therefore no critical point as well on the second line. And the third line give you the line that we have. It is y equal to negative 5 over 3x plus 5. So you have to substitute this y into the equation here. Okay, so as you can see in the result here, so you have to substitute the y into the function. So you have only the expression in terms of x. So let's say I skip that one, so please do it yourself. So when you substitute all the y, so you have to substitute the y by this linear equation, this one y, and then you have this negative 6x and negative 3y, and then with some when you simplify, you have the function in terms of only x, which give you negative 5x squared plus 14x minus 8. Okay, and then now we want to find the critical point along this line. So you have to differentiate respect to x. So negative 10x plus 14 equal to 0. So we solve for x, so you have x equal to 14 over 10, so 7 over 5. So that is the x. So when you obtain the x here, so you can evaluate, you substitute the x into here, so you can obtain for y, so negative 5 over 3, x is 7 over 5 plus 5, and you have negative 7 over 3 plus 5, will give you minus 7 plus 15 over 3, y is 8 over 3. So the critical point at this line, this line is 7 over 5, 8 over 3. Okay, so this is another point that you have to take into account. So far you have 1, 2, 3, 4, and 5. So you have to check all the 5 points, which one will give you the highest value and the smallest value. So based on the 5 points that you obtain, critical point, the vertex, and also the critical point along the lines, along the boundary line. So you got 5 here, so you have to evaluate the function. So you have to replace all the point, substitute into the function here. So you have to substitute here. So when x0, y0, so the function gives you 7, and at 3, 0 will give you negative 11, and so on. And then you have to compare which one is the highest one. The highest one is 7, so 7 is the absolute maximum. So absolute maximum value is 7, where it happened at 0, 0. That's how you can also justify the point and also the value here. Okay, and the smallest one happened at negative 11, and it happened at 3, 0. So this is another way of writing that show you the value and also the point. So it is up to you which version that you want to use. Okay, so that is how you deal with the absolute extrema for bounded region. Okay, so in this case you don't have the you don't need to apply the second derivative test. So for the next one we want to focus on the absolute extrema for open and unbounded region. Okay, this one is just like local extrema. Okay, maybe if I explain this, so it's a bit confusing, so we try to look at the example. Okay, so you are given a function, and then you can see that this is just a kind of open region because we only consider x, y positive. This is open, okay? So it just on the first quadrant because x positive, y positive. So it is at the open region. So if you try to sketch the region, so we only consider x positive and y positive. So that is only the region. So this is open region. Okay, but not include, because you can see there is no equal sign, so not include the y-axis and x-axis. Okay, so we can see this just like a dash line maybe. Oops. So we can this one. Okay, not include the x and y axis. Okay, now how can we deal with this problem? So the function is given by x cubed plus y cubed minus 6xy. Okay, and then just like the first two steps, we have to find the critical point. So differentiate respect to x, and then differentiate respect to y. Okay, y I'm putting the equal to 0 because I want to find the critical point, so you have to equate that by 0, and you have to solve this equation simultaneously. So here maybe I can see that 3, I start with the fx 0, 3x squared equal to 6y, and I can have y equal to 1 over 2 x squared. So then I substitute the y here into the second equation. Okay. So y squared is 1 over 4 x 4. So then I can have 3 over 4 x 4 minus 6x equal to 0. And this one you can have the x here and have the x here. to cancel straightforward. So away, you have to factorize first. So factorize the x, so you have 3 over 4x minus 6 equal to 0. Then you can have two values of x, right? 0 and x equal to 6 times 4 over 3. So you got 8. So is that correct? 6, 4. Okay, so this one should be cube, right? So we got cube here. Okay, and x is 2. So I obtain that I0. So when x equal to 0, so I substitute the I0 into the y here. So when x0, y also 0. And then when x equal to 2, so y equal to 1 over 2, 4. So you got 2. So the critical points, we got 2 points here, is at 0, 0. And the other one is 2, 2. Okay, just like the previous one, please always check that the point is inside the region or not. So 0, 0. 2, 2 is fine. So 2, 2, x2, y2 somewhere here. It is in the region. But 0, 0 is because we have there is not equal sign here. Not include the x and y axis, so not include the y0 and x0. So meaning that 0, 0 is not in the region. So we don't count that one. So we only have 2, 2 here. So here, since there is no boundary, it is open region, no boundary, so you cannot do the same as the absolute extrema. For closed, you cannot have the specific line because it is open, so you don't need to investigate for the point along the line. So the process is just like local extrema. Once you done once you obtain the critical point, so you can just determine whether it is min or max. Okay, we're using the second derivative test. So for this, for open region, the process is just like a local extrema. So here you need to apply the second derivative test. Because if you just substitute the values, so you're not sure whether that one, the value should be the most, the highest, the max, or the mean. So you need to use the second derivative test to help you to investigate or to determine the behavior of the point when it is max or min. Alright, so here for the second derivative test, so you need to have the second derivative for the function. So you have the fxx, fyy, fxy. Okay, fxx you have to use from here. Differentiate that again with respect to x, so you got 6x 0 minus 0. Fyy, then you have to use this one. So differentiate this again with respect to y, so you have 6y. And fxy, so let's say I'm using fx and differentiate with respect to y, so you have minus 6. Okay, and then your Hessian metric. Remember what doesn't matter, sometimes they use G, sometimes they use Hessian, doesn't matter, as long as you know that one is the Hessian metric. Determine the value. So the formula is fxx fyy minus fxy squared. Ffx is 6x, fyy is 6y, and then fxy is negative 6 squared. And this will give you 36xy minus 36. Okay, so now you have to determine the value h or g at the point 2, 2. So 36, 4 minus 36, and of course this gives you positive. Okay, so positive means that you can have max or min. Okay, so if your G or H is positive, so there's two possibilities, whether max or min. And to know whether it is max or min, you have to find out the value of fxs. And you obtain that the fxx is here. Okay, and you replace the x equal to 2, so you got 12, so it is positive. Remember the procedure to determine whether it is max or min. So this is positive, and you are smiling, and you have the minimum here. So you can see that F22, and when you evaluate F22, you substitute x2, y2 here. F22, you got 8 minus 6, 4. You will have negative 8, right? So the value is minus 8 is a local minimum. We can just say it is a local minimum, so we cannot say it is absolute. But since there is only one point here, and definitely you can say this one, negative 8 is the absolute minimum. Alright? You can see that there is no local max and no saddle. There is no any other point, so you can definitely say that whatever that you have here is the absolute minimum. But if you have any other points, you got more than one point, then you have to find out what if it is the highest one is, let's say you have another point which is negative 8, and the other one is positive 8. So you can see that negative 8 is the absolute mean, and the positive 8 here is the absolute max. That is for open region. So remember, for the operations of the process, the idea is just like local extrema or relative extrema.